So in this video, we are going to learn some quick rules for computing derivatives. If you recall, in the previous chapter, we used the limit definition of the derivative, which was often kind of tedious and, complicated. So these rules are going to be a nice relief. First, I just want to remind you of some of the new basic rules that we have. The first rule is called the constant rule, and it just tells us that the derivative of a constant is always equal to 0. So if this is any number, like 5 or 7, the derivative is just 0. And we should expect that because the function y equal c is just a horizontal line, so all the tangent lines will have slope 0 also. The power rule tells us that the derivative of a power function is equal to the power, so n times x raised to the n minus 1 power. So we just drop this by 1. And next we have the sum difference rule, and that just tells us that the derivative of a sum is equal to the sum of the derivatives, or similarly for the difference. We also have the constant multiple rule, which tells us the derivative of a constant times our function is equal to that constant times the derivative of the function. And finally, we have the exponential rule, which tells us that derivative of the exponential function with base e is equal to itself. So let's do some examples. So differentiate the function. So here I have a horizontal line. So we expect all the tangent lines are also going to be exactly the same horizontal line. And we know horizontal lines have slope 0. So we expect this derivative to be 0. And as the constant rule tells us, y prime is equal to d dx of 10, which by the constant rule is just 0. For the line y equal x, okay, so remember this is just the line through the origin, and it has slope 1. So same holds for all of its tangent lines. They're exactly the same line. Slope will be 1, okay. In this case, we can use the power rule. We can rewrite this function as x raised to the first power. So this will be 1 times x to the 1 minus 1. So that's just x to the 0, or just 1. So the derivative of x is just 1. So here's the function f of x equal x to the 8th. The derivative, so f prime of x, I'm just going to use the power rule. And that's just going to be 8 times x to the 8 minus 1. So that's just 8x to the 7th, and we're done. I just wanted to point out as a side note that I can keep computing derivatives. For the second derivative of f, I would use this notation, f double prime of x, and I would apply the power rule again. That would give me 56 x to the 6th. I could keep going. I could compute the third derivative, so f triple prime of x, and that would give me, again using the power rule, 6 times 56, 336 x to the 5th. And you can also keep going and compute fourth derivative, etc. So one situation where that might be useful, computing multiple derivatives, an example would be, let's suppose that this function represents the motion. This was the equation of motion of a particle. So for instance, this was s equal f of x equal x to the 8th. Then the first derivative here would actually give me the velocity. So this would be velocity at time t, or time, I guess, in the x in this case, if x represented time. So this would be the velocity, the first derivative, and the second derivative would give me the acceleration. Okay, so let's do another example. So suppose g of x is equal to 1 over x to the 7th. So in this case, g prime of x is equal to, I'm going to rewrite this function with negative exponents. So I haven't taken a derivative yet. I'm just rewriting it. Now I can use the power rule. So this would be negative 7 times x to the negative 7 minus 1. So that's negative 7x to the negative 8, which can be rewritten as negative 7 over x to the 8th. And we're done. And here's another example, example E. F of x is equal to the cube root of x raised to the 4th power. So this derivative, f prime of x, is, I'm just going to rewrite my function, the cube root of x to the 4th, which can be rewritten as x to the 4/3 power. And this is, and if I use the power rule here, I have 4/3 times x, and then I have 4/3 minus 1. So this is equal to 4/3 x to the 4/3 minus 3/3, which is equal to 4/3 x to the 1/3. Okay, and we can rewrite that as 4/3 cube root of x, and then we're done. Okay. So I want to point out that if you're not remembering this quite, if this isn't fresh in your mind from algebra, remember that x, if I have the nth root of x raised to the mth power, this can be rewritten with rational exponents as x over to the m over n. So let's move on. So in this case, y prime is equal to the derivative of this function, and I'm going to use the sum and difference rules to break this into a sums and differences of derivatives, and I'm also going to pull out the constant multiples. Okay, so let's do that. So y prime is going to be 3/5 times the derivative of x to the 5th minus 7 times the derivative of x, 1 over x to the 10th, plus 3 times the derivative of x minus the derivative of pi and plus the derivative of 2 to the 18th. So all I've done here is I broke the derivative up across the sums and differences, and then I also pulled out the constant multiples, and it led to this expression that we have here. Okay, so now I'm going to finish off the derivative. Using the power rule, this becomes 5x to the 4th minus 7 times, and remember this guy can be rewritten as x to the negative 10. So its derivative is going to be negative 10 times x to the negative 11. And then here I have plus 3. The derivative of x is just 1 minus, this is a constant, so the derivative is 0. This is a constant. Don't be fooled by the 18th power there. That's just 0. The only thing I have left to do is just clean this up a little bit. I have 3x to the 4th plus 70x to the negative 11th plus 3. And you can even write that without negative exponents if you want. and then we're done. So that's it. Okay, so let's do one more example. My function is h of x equal to 3e to the x minus 2 divided by the 7th root of x to the 5th plus e to the 4th. So I'm going to use a slightly different notation for h of x, just to get you used to the different notation. The prime notation for the derivative is h prime of x. You might also see it just someone write y prime, that's fine too. And you can also use the notation dh dx. This just means the derivative, this is the derivative of h with respect to x. Okay, so let's start. So I'm going to start by doing what I did before. I'm going to break this up across this difference in the sum, and I'm going to pull out the constant multiples, and I'm just going to rewrite the derivative. So I have 3 times d dx of e to the x minus 2 times d dx. Okay, and before I write this guy down, I'm also going to note that 1 over the 7th root of x to the 5th can be rewritten as 1 over x to the 5/7, which can be rewritten as x to the negative 5/7. Okay, so in this case, I'm going to rewrite this guy as x to the negative 5/7 power, and then plus the derivative of e to the 4th. Now calculating my derivatives, I have 3. So remember that derivative of the exponential function is just itself. It's its own derivative. Minus 2. I'm going to use the power rule on this function, so that's negative 5/7 times x. And then if we have negative 5/7 minus 1, that's going to be negative 5/7 minus 7 over 7, which is negative 12/7. That's all up in my exponent. And then this guy, don't be fooled, this is just a constant. It's about 2.7 to the 4th, so it's just 0. Derivative of a constant is just 0. Okay, and let's just clean this up a little. So my final answer is 3e to the x plus 10/7. And I can write this guy back down in the denominator as x to the 12th. And we take the 7th root. And then that would be my final answer.